I'm going to work through two examples of using the energy principle, one at low speeds and one at relativistic speeds. So for the first one, let's say that we have a nice heavy steel ball launched into the air by a massive spring launcher. The ball is initially at rest but leaves the spring with a speed of 20 meters per second. Let's figure out how much work is done on the ball by the surroundings. Now, I really want to point out that it's important to do the problem-solving format here and not to just jump right into things, because a lot of times what I've seen students do in this situation is they'll try to find an equation that involves energy and springs. And first off, we haven't introduced that yet, but second off, it's not needed here. And thirdly, you don't actually even have enough information to use a spring equation for the energy. So it's best just to start writing things down following the format. So we have our sketch here, and with energy problems, you need to include a before and after. All right, so your sketch and everything should include a before situation and an after situation. We start at rest, we have some velocity. I've chosen my system to be the ball so that my surroundings are just the earth and the spring. And here we have the free body diagram, and I've indicated the direction of the net force. List all of our knowns and unknowns, and then the equations. One other equation that we might need is the equation for work, which is work equals F dot delta R. Okay, so actually the thing that's going to direct your problem the most are these energy bar charts. So take a look and just draw out the energy bar. So my kinetic energy initial is 0, so I'm just going to indicate that with a little horizontal line here. There's no kinetic energy. Now, the force is in the upward direction, as is the movement, the motion. So since force and displacement are in the same direction, I'm going to have positive work. Another way to think of this is the velocity of the ball is increasing because of the force. Therefore, the kinetic energy is increasing. That means we have to be adding energy to the system. So that's going to come in the form of work. And then we have kinetic energy final is just going to be the sum of these two. Now, you may notice that I haven't included the rest energy. And the reason is whenever we're doing a low speed approximation and there's really no changes of the particles, we're just going to have a rest energy term that is the same on both sides. And that rest energy term is going to be many, many orders of magnitude larger than any of these values. So for low speed problems where there's no change in the particle identities, in other words, whatever the particle is in the beginning, it's the same thing at the end. You don't have a helium atom splitting into two hydrogen atoms and changing identity. Anytime there's no change in mass, we can just leave off the rest energy term. So this bar chart actually gives me my equation. Kinetic energy initial is 0. I don't need to include that in the equation. The only non-zero terms are the work and the kinetic energy final. So my equation for solving this problem is work equals K final. There you have it. I have enough information to solve for the kinetic energy in the final case. I've got the mass and I have the velocity. I don't need anything else. So my strategy is simply to plug in M and V to find K final, and from that I'll find W. Unfortunately, when I get down to the bottom of the screen here, my handwriting, the sensor gets very ugly, so I'm not going to try writing the rest of this, but finding K final, and then from that find the work. So my mass was half of a kilogram, 0.5 kilograms. My velocity is 20 meters per second squared. So this comes out to be 100 kilogram meters squared per second squared. And let me play around with this. So I know that kilogram meters per second squared is newtons. So kilogram meters per second squared, that leaves me 1 unit of meter, and the Newton meter is the joule. Now the work is equal to K final, so the work done is just 100 joules. So I've actually already carried out the unit check. Answer. So my unit check is right here, here, and there. Is this a reasonable answer? Well, if I take a look at the equation sheet, I see that K for a 90-mile-per-hour baseball is approximately 100 joules. So since this is a pretty hefty steel ball moving at 20 meters per second, this isn't an unreasonable answer. So my answer is close to this, equal to it, and is reasonable. All right, so let's take a look at a relativistic problem. And let's say that we have an electron in the Stanford Linear Accelerator, and it's got some velocity near the speed of light, 0.995 times the speed of light. That's 99.5% of the speed of light. And the particle accelerator speeds these particles up by exerting electric force on them. And so we've got some force, and it moves through a certain distance down the beamline. What is the final speed of the electron? Now, since my speeds are close to the speed of light, I cannot use the low speed approximation. One other thing you'll see is that a lot of times it doesn't make sense in these cases to break out the kinetic energy necessarily and the rest energy. It just makes more sense to deal with the total energy. So if I go ahead and first I've set everything up, I've drawn my before and my after. Here's my system, the electron. The surroundings are the accelerator and the Earth. And the assumption I'm making is that the gravitational force is negligible compared to the force of the accelerator. mg for the electron is 10 to the 29, which is much less than the 10 to the negative 13 newtons that's exerted by this accelerator. So the change in energy due to gravity, if we look at where in the decimal places of our answer this is going to occur, changes due to this guy are going to be several places beyond the significant figures that we need to write down. So I draw out my free body diagram, list out all the knowns and what I'm trying to find, and then write down any equations that I might need. So I'm going to use the total energy equation here. I could write down the relativistic kinetic energy equation, which is gamma minus 1 mc squared, but it turns out that in this case it really doesn't gain me anything, and it just adds a little bit of algebra. And then here we have the energy principle equation. So let's write down my energies here. So I've got some amount of initial energy. I got positive work. I know that my work is positive because the force and the displacement are in the same direction. So the dot product is going to give me a positive number. So the total energy is just going to be the sum of my initial kinetic energy plus my work. So I'm going to end up with larger energy at the end. So from this diagram, I can actually write down what my energy conservation equation is. All three of these are non-zero terms, need to be included. So A initial plus work, we have gamma initial mc squared plus the work, which is just the electric force dotted into change in position, and that's going to be equal to gamma final mc squared. We need to include the subscript of initial and final on gamma because since gamma depends on the velocity, we have different velocities. That's going to give me some different answers. So let me break this out and calculate the work off to the side. So the work, which is F electric dotted with delta R, the force is 5 times 10 to the negative 13, 0, 0 newtons. Dot that into my 5, 0, 0 meters. And so again, work is a scalar quantity, just comes from multiplying each component together and then adding them up. So I'm going to get 2.5 times 10 to the negative 12 Newton meters plus, and the y components give me 0. The z component gives me 0. So the work done by the electric field on the electron is 2.5 times 10 to the negative 12 joules. So, start plugging things in. Gamma here is 1 over square root of 1 minus. Now remember that this is v over c, and since my velocity is in terms of c, this term in parentheses here is just the fraction of the speed of light. And so that's why giving your answer in terms of c actually makes the math just a little bit easier. Times the mass, c squared, plus 2.5 times 10 to the negative 12 joules. Mass electron, c squared, is equal to gamma final mc squared. So I'm trying to find the final velocity. So let me solve this for gamma final, and then once I've solved for gamma final, I can then go ahead and solve for v final. So if I go ahead and plug this term in, I get actually a factor of 10. Okay, gamma initial is 10. So let me plug that in, and then I'm going to divide both sides by mc squared. I get that gamma final is equal to 10 mc squared plus 2.5 times 10 to the negative 12 joules all over this term right here, mc squared. And plugging these results in, we end up with gamma final is equal to 40.9. Notice that the units have all canceled out because we've got units of joules up top, joules in the denominator, those cancel out. Gamma is a unitless number, one of the few cases where it is unitless. So gamma final is 1 over square root of 1 minus v over c squared, 40.9. So let me just cross multiply and switch the place of the 40.9 with this denominator to get that 40.9 is equal to the square root of 1 minus v over c squared. And I can go ahead and square both sides to get, I'm sorry, this is supposed to be 1 over 40.9. So squaring both sides will give me 5.98 times 10 to the minus 4 equals 1 minus v final over c squared. And then this ratio, let's see, subtracting 1 from both sides, I'm going to get negative 0.9994 is equal to negative v final over c squared. I can multiply both sides by that, and then just take the square root of both sides. I'm right there. V final is equal to 0.9997 times c. There's my final velocity. So, checking my answer, let's see if my units work out. Well, v over c has units of meters over seconds or meters over seconds. Those cancel out, and so this is unitless. C has units of meters per second. V has units of meters per second. So the units are looking pretty good. In terms of reasonableness, is this a reasonable answer? Well, my original velocity was 0.995. So V initial was 0.995 c. V final is 0.9997 c. This is reasonable because the work done was positive. The particle was speeding up. The particle was speeding up because of the force. So V final had to be greater than V initial, but it also needed to be less than C. But V final needed to be less than c, which it is. So both these conditions are satisfied. V final is larger than the initial velocity and less than the speed of light. Anytime you get a velocity larger than the speed of light, you know that something's gone wrong.